Hi, I'm Josh Gardner from the University of Washington. I'm here to share our work, Cross-Institutional Transfer Learning for Educational Models, Implications for Model Performance, Fairness, and Equity. This is joint work with Renja, Kwan, Chris, and Renee. Modern machine learning models typically require large training datasets to train a model and achieve good performance. In practice, it is often true that separate datasets, representing different observations but with the same set of features, might be available to many different actors or institutions. These institutions often also all would like to train a model to perform the same underlying prediction task with this same feature set. For example, many banks may want to predict creditworthiness using the same feature sets collected from customers at their institution. Typically, institutions would simply train these models on their own. However, it's well known that most machine learning models often require large data sets during training to be most effective, meaning that multiple actors or institutions may benefit from leveraging more data when training their models. However, there are many challenges to this kind of collaboration, even when actors would like to collaborate and improve their own models. The classical approach to this problem would be to simply centralize the training data and train a single shared model. However, this is often impractical or even prohibited due to data privacy constraints. For example, privacy restrictions in many countries prohibit the sharing of sensitive data such as medical, financial, or educational data. Other paradigms have increasingly become available due to advances in both machine learning methods and systems. In many of these paradigms, data can stay at the institution that hosts it and is never shared. Instead, iterative rounds of communication occur between institutions where some information about the model is shared, for example, gradients during training or the model weights of the client institution. These models can be aggregated into a global model, which might be called federated learning, or the individual models can be communicated directly back to each institution, as shown here, to be used at the institution in whatever way they decide. For example, by using another institution's model parameters or building an ensemble of those models. This kind of distributed training can confer many benefits, since institutions might be able to learn from data beyond their own locally available data by receiving model parameters trained at other institutions. For example, it can provide better predictive accuracy to each institution by leveraging other institutions' data, potentially increasing both the size and diversity of the training data. It can do so with sometimes provable guarantees of privacy, which are not the focus of this talk. However, the empirical consequences of using this procedure, which we refer to as cross-institutional transfer learning, are not well understood, despite its widespread potential for use. This lack of understanding applies to the overall performance of cross-institutional transfer models, but also to the fairness of these models, since different institutions often represent very different populations. There could be downstream consequences from using such models which are not present when only local models are used. It might be true that access to more diverse populations and larger training data sets improves performance via transfer, but it could also be the case that models which are trained on dissimilar populations may transfer poorly and negatively impact performance at a given institution or increase disparities between sensitive subgroups. These are fundamental questions which have not been evaluated in any prior study, despite widespread opportunities for cross-institutional transfer learning in many application areas. Our study addresses three main research questions in this space in the context of a case study in higher education dropout prediction. Our research questions are as follows. First, how does cross-institutional transfer affect performance relative to a local model? Second, how does cross-institutional transfer affect the intersectional fairness of the resulting model? Finally, is there a trade-off between model performance and fairness under cross-institutional transfer? Addressing these three questions can provide important empirical insights into the emerging paradigm of cross-institutional training and can provide useful guidance on how, if at all, cross-institutional learning can be used to improve model performance, fairness, and equity. In this talk, we'll focus primarily on the results relevant to the first two questions, since we feel these are the most significant gaps in the current understanding of cross-institutional transfer. We conduct our study in the context of higher education dropout prediction. In particular, we evaluate models designed to predict whether first-year bachelor's degree students enrolled at four-year degree-granting institutions in the United States will re-enroll the following year. This is a prediction task that is widely considered in both the academic literature and in practice at universities, where students at risk of not returning might be offered extra support, in order to ensure that they can continue on the pathway to graduation. This also matches the National Student Clearinghouse's definition of student dropout and is mandated for federal reporting for accredited universities in the U.S. We consider the most restrictive scenario where only a single round of weight sharing is allowed between institutions. The dataset used in our study represents a wide range of enrollment sizes, demographic compositions, and first-year retention rates, and is drawn from 4 universities which we anonymize as institutions A, B, C, and D, and these are summarized below. We note that the features we use are raw features extracted from the student information systems at these 4 real institutions. These are features that almost every university collects during the normal process of student application, enrollment, and course registration and completion. This makes us a strong candidate for cross-institutional transfer learning. To evaluate the impact of cross-institutional transfer, we conduct a set of experiments where we vary 3 factors: the functional form of the predictor, the cross-institutional transfer type, and the model selection rule for stacking experiments only. We will focus specifically on the transfer type results in this talk, but more detailed results for the other experiments are in the paper. In this talk, as in the paper, our main results present only the gradient-boosted trees results. However, we share results for the other model types, regularized logistic regression and neural networks, in the supplement to our paper. Our results are consistent across model types, but gradient boosting generally performed best, so we focus on it here. Next, I'll provide some detail on the 4 types of cross-institutional transfer that we consider in our experiments. Recall the model of transfer we introduced earlier. In practice, there are many potential variants of this setup which use different training datasets, models, and techniques for using or combining models from across institutions. The simplest such method is a local model. This is the standard approach where institutions train a model on their own local data and use it for prediction. The second cross-institutional transfer procedure we evaluate is called direct transfer. Here, an institution uses a single model trained at another institution. In this setup, no local model is used. Only the model from another institution gets used. The third approach we consider is voting transfer. Here, an institution receives a set of models trained at all other institutions. Then, the predictions of all these external models are combined using a zero-shot voting procedure where the predicted probabilities of each model are aggregated to form a single prediction. This is also sometimes called output space ensembling. Note that this is a zero-shot approach. It requires no local training data nor a local model. The final approach we consider is stacked transfer. Here, all models are available to all institutions. There can potentially be many more than just one model per institution, for example, if many models are trained and shared by each institution. Then, those models can be combined by appending their predictions to the input set of features and training a stacked model. This requires the most collaboration, but also could be interpreted as making the most information available to each institution. We vary the 3 previously mentioned factors, including the 4 types of cross-institutional transfer just described, across our dataset of 4 institutions. Then, we compare the results, which I'll discuss next. I'll present our main findings here. First, we address research question 1, which is about predictive performance under cross-institutional transfer. As shown here, we find that while direct transfer has inconsistent performance, voting transfer, the zero-shot procedure that requires no local model, is competitive with the local models at all institutions. Furthermore, stacked transfer, where all models are available to a given institution and it can use the outputs from other institutions as features at both training and inference time, does not provide additional benefit over voting transfer. This is an important finding as it suggests that institutions in our study with no local training data could use voting transfer to utilize models with similar performance to their local models. This could provide under-resourced institutions with a meaningful way to adopt models from higher-resourced institutions using only existing data already collected by the institutions. Here, we also show on the right the confidence intervals for the transfer gap, which we define and refer to as delta AUC. These confidence intervals include 0. This formalizes our claim that we cannot reject the null hypothesis that there is no difference between the voting transfer model and the local model, nor between the stacked transfer model and the local model. Next, we investigate the fairness of models under cross-institutional transfer. We know from many studies that subpopulation effects can be masked by only looking at average performance. So, we explore intersectional subgroups of sensitive attributes. Here, underrepresented minority status and self-reported student gender. On the left, we show the test performance across all intersectional subgroups for these attributes for each institution and transfer type. Our results show, perhaps unsurprisingly, that there's considerable difference in the predictive performance of all models across sensitive subgroups as measured by the maximum gap between any two groups. However, the surprising finding here is that there's no discernible fairness impact from cross-institutional transfer. Particularly, in the case of zero-shot voting transfer, this is quite surprising. Training models on a different population of students from other universities and directly transferring them to another institution does not affect performance disparities and sometimes even decreases these disparities. We present some more exploratory findings in the paper related to the lack of trade-off between fairness and accuracy, the importance of using intersectional analysis versus one-dimensional fairness analyses, and the impact of regularization on our results. We also discuss the limitations of our study. In particular, our conclusions are limited to the datasets used in our case study, which are a particular set of universities situated within the U.S. educational system. Further research is needed to understand how these findings apply to other institutions in higher education, as well as how these apply to other cross-institutional transfer contexts. With that said, the main takeaways from our findings are as follows. Cross-institutional transfer can be as effective as local model training, even when no local training data is present at a given institution. This transfer has no discernible impact on disparities between sensitive subgroups in our study, which looked at underrepresented minority status and self-declared gender, even when differences between transfer populations exist. And as I mentioned earlier, more research is needed on this emerging paradigm, including methods to improve the transfer adaptation, the impact of privacy-preserving ensembling, and data work to enable more institutions to participate in this research. Thanks for listening. You can find our paper in the FACT 2023 conference proceedings and on arXiv, and our code is on GitHub. There's a link in the paper.